Good morning, everyone. So, myself, Dr. Anju Mishra, I'm Associate Professor in the Department of Information Technology, Akgec Engineering College, Ghaziabad. And today, the topic that I'm going to discuss is the dynamic programming. And we are also going to see that how we can solve certain problems using dynamic programming. So, let's start for today. So, when I talk about the dynamic programming algorithm, basically this is an algorithmic design paradigm where we are solving the complex problems by breaking them down into smaller sub-problems. So, if you have one single problem, you are breaking that problem into sub-problems which are simpler to solve, and once you reach to the simplest level of the problems, then we are solving those problems and then building up the solutions to find out the solution of the main problem. So, this is the core idea behind the dynamic programming approach. Now, when I talk about the dynamic programming background, it is a kind of similar to the divide and conquer approach. In divide and conquer approach, we also divide the problem into sub problems, and then we try to recursively solve and build up the solution for the final problem. In a similar fashion, in the dynamic programming, we are also following the same steps, that we are dividing the problem into multiple sub problems, and once we are able to reach to the simplest level of the problem, we are solving them and then finally building up the solution. Now, what is the basic difference between the dynamic programming approach and the divide and conquer approach? So, when we talk about the difference, the major difference is that in divide and conquer approach, what we do, that we are recursively solving each and every sub problem to find out the solution of the more complex problem. But when we use the dynamic programming approach, whenever we are solving the simplest problems, we are storing that solution for future use, right? So, there is a kind of a table data structure that we are using to store our solved problem solutions there. And whenever the similar kind of problem is encountered, we are not again solving it and wasting the computational time. Rather, we'll do the table lookup operation and we find out the value from the table. If the value of that particular sub problem is not available in the table, then only the dynamic programming approach solves the problem, and again, once again, it stores the solution into the table data structure. So, that way it is actually minimizing over the time taken by the divide and conquer approach for solving each and every sub problem which it encounters while it is solving a particular problem. Now, when we talk about the dynamic programming, there are two ways to store the result. There could be one approach where we are moving from top down manner, and this kind of approach is called as the memorization. The second approach is called as a bottom up approach. So, as you can see that we are solving the sub problem and then building up the solution from the bottom up manner, and this kind of approach is usually called as the tabulation method. These are some of the example problems that we can solve using dynamic programming approach. So, like the Fibonacci numbers, then diff utility, or the longest common subsequence problem we can solve using dynamic programming. Then Bellman-Ford is another problem that we can solve using dynamic programming, and we can find out the solution for the shortest paths. Then Floyd-Warshall solution we can also find out then the problem of edit distances and matrix chain multiplication, which is again an important problem in the domain of computer science, that we can solve effectively with the help of dynamic programming approach. Now, what are the common steps when we proceed to solve a problem using dynamic programming? So, there are majorly 4 different steps that we need to follow to solve a particular problem using dynamic programming approach. The first step is called as the identify the sub problems. So, in the identification of sub problems, we need to divide the problem, and we are able to find out the sub problems, and that makes the complete first step for the solution building. And then in the next step, we are solving those sub problems, and then we are storing the solutions into the memory. So it could be a tabular data structure that we are using in the memory to store up the solutions which we already have found out. And then finally, in the third step, we are building up the solution. So this is the third step where we are building up the solutions in a top down or a bottom up manner by doing the table lookup operations. Finally, we are avoiding the redundancy. So avoiding the redundancy is an important aspect, and basically the most important difference between the dynamic programming and the divide and conquer approach. In this step, what we are trying to do, that we are not trying to solve each and every sub problem explicitly as we do in case of divide and conquer approach. Rather, what we do, that we are storing the solution already. So whenever we are encountering a sub problem and we need to solve it, we are first going to see the table data structure. So if we are able to find out the solution there, then we are picking up the solution from there directly, and there is no need to solve this particular sub problem for us. And then we are moving to the other sub problem. So this way we are actually avoiding the redundancy while we are solving the sub problems. Now, one important question that we can ask is when to use the dynamic programming. So how do I know that when I need to apply or solve a given problem using dynamic programming approach? So there are two major characteristics that we have to find about. First thing is that the problem must have an optimal substructure. So this is the first characteristic. If the problem can be divided in such a way that we are able to find out the optimal substructures, then dynamic programming can be applied on such type of problem and we can solve it. The second thing that we need to see is that specifically, are there overlapping sub problems? So if we are able to find out that there are so many overlapping sub problems and for which we need to provide the solution, then dynamic programming is more competitive as rather than applying the divide and conquer approach. So if you are not able to find out the overlapping sub problems, then in that case you can apply the divide and conquer or the dynamic programming, but specifically dynamic programming is more approachable and more appealing when we are having a lot of sub problems which are repeating again and again. So that way we are actually optimizing over the time taken by the algorithm to find out the solution quickly. Now we are going to see one example how dynamic programming can solve the problems, and for this the first example that I have taken up today is to find out the Fibonacci sequence. So for example, if I have been given a problem where I need to find out the Fibonacci sequence for a particular number. For example, if I have been given one, I need to find out the solution of f5, right? So how dynamic programming is finding out this solution? So for this, for the convenience of visualization, what I will do, that I will show you the solution with the help of a kind of tree sort of diagram, so that we are able to understand that what are these steps the approach is going to make up while finding out a solution for the given problem, right? So for example, if we need to find out f5, then as we already know that in the dynamic programming approach, we must be able to divide the problem into optimal substructures or the optimal sub problems. So I need to first divide this into finding out the solution of, for example, the f5, how I can find out a Fibonacci number. So for that I need to add up the two previous terms in the Fibonacci sequence, and that makes up the number here. So to find out f5, I need to recursively find out the solution for the previous term, which is f4, for example, and f3, right? Now if I need to find out the solution for the f4, I need to see, or I need to look up its previous terms. So for F4, I need to find out F3 and I need to find out F2, right? Similar ways, the F3 solution, I do not know that what is the solution for F3 and F2. So I again need to, find out the solution recursively and need to see the previous term solution. So for F3, it will be F2 that I need to compute. Then I need to compute F1, right? And similar ways, again for F2, I need to first seek the solution for F1 and F0, right? Now for F1, again, I can directly put up the solution, or I can again, take it to F0, solution of F0. So this, these are actually the base cases. So we can put directly solutions here. So there is no need to, find out the solution explicitly. We already know that what is the value of F0 and F1, right? So we can directly put solutions here. And as you can see that while we are, descending into the tree and recursively, breaking the problem into sub-problems, there are many steps where we are having, similar kind of sub-problems. So as you can see for F3, we are having one instance here and we are having a sub-problem instance here, right? So F3 solution needs to be calculated 2 times if I am using a dynamic, this divide and conquer approach. But for example, if I'm using the dynamic programming approach, I can save on this time and reduce the computational, resources by only computing the solution of a sub problems once, right? For F2, I again need to find out the 2 previous terms, which are F1 and F0, for example, right? And for F3 again, I need to find out the solution of F2 and then I need to find out solution of F1, right? And F2, I need to find out like F1 and then F of 0. So that way we can see that for again F2, we are having one instance which need to solve here, and then we need to find out and solve this sub problem for F2 again. And again, when we are moving towards this branch of the tree, again this F2 solution I need to find out, right? So in case of dynamic programming, what we do that, for example, if I'm using a bottom-up approach to build up the solution, what I will do that I will try to solve these problems and then I'm putting that solution into a table data structure. So for example, for F0, I know that the solution is 0, right? And for F1, it is 1. So for this F2, I need to solve here F0. So the solution for F0 is again 0, and you can find out that for F2, I can find it out as the solution of this added to this, right? So 1 plus 0 is 1, right? So that way we are building up the solution towards the upper part, and we will be eventually able to solve the problem again. The next problem that we are going to discuss here is the knapsack problem. So knapsack problem is one of the most important problem when we are going to study the algorithm design paradigms. And knapsack problem can be solved using the greedy approach or the dynamic programming approach. So I'm going to discuss that what are the basic steps that we need to perform here to find out the solution of knapsack problem using dynamic programming approach. So as you can see that, for example, one problem instance is given to us where I am having the capacity of the knapsack is 9. So again, to repeat the problem, I would just say that in the knapsack problem, we have been given a knapsack with a limited capacity, which is denoted here as M, and we have been given n number of objects with us. Every object is having certain weight, which is represented as Wi, and associated profit or the value, which is given here as Pi. Okay, so the ith object profit is, I can find it out from Pi I can find out here from the profit of the nth object, or sorry, ith object from the total n objects that have been given to me, right? Similar ways, what will be the profit? Associated profit I can find out as Wi. So I here is nothing but the index of the, or the number of the object that I am selecting, and I'm assuming that I have kept all the objects in a particular sequence. So in this way, for example, if I apply the indexes here 1, 0, 1, 2, 3 and 4, 0, 1, 2, 3 and 4, then I can, if I set I is equal to, for example, 0, the Pi in this case would become the profit associated with the first object. So this is 1, and if I refer to Wi, where I is equal to 0, this refers to the weight of the first object, right, which I can find from this W vector. And as I can see that for the first object we are having the weight and the profit as 1 unit. Okay, so this is the problem that we have been given. Now the basic equation that has been utilized in dynamic programming approach to solve the knapsack instance is given like this. So for finding out the kth entry, right, k of I and W, I need to find out maximum between ki minus 1 W and ki minus 1 W minus Wi plus Pi. So this is the one term and this is the another term. Whichever is maximum in this case, okay, I need to compute these two terms first, and then I need to make a decision whichever is maximum out of these two, I am keeping it or setting it as the entry in the table. So as we already know that in dynamic programming approach, I need to create a table to store the sub-problem solutions. Let us see how we are going to create this problem here. So to create a table, I need to first decide on the dimensions of the table, and as you can see that we have been given 5 objects here. So the table size should be with a dimension of 6, right? 6 objects we have been given. So I'm going to have 6 rows for 5 objects. One object we are taking up, or we are assuming it up to solve the problem in a smoother way, right? So or I can also say that for n objects where n is referred to 5, I need to take one extra row for computational purpose, so that the equation is smoothly going to be applied, and we are able to understand that how we are computing those entries, right? Similar ways, so we are going to have 6. How many number of columns we are going to have? So number of columns depends upon the maximum capacity of the next knapsack. So here M is set to 9. So this is the maximum capacity of the knapsack, right? And these many number of columns we have to take up into the table. And again, as we have done in case of the number of rows, we have taken up one extra row. Again here for the computational purpose, we will be taking one extra column, right? So in this case, the number of columns will be 10, 9 plus 1. 9 why? Because we are having the maximum capacity as 9 of the knapsack, right? Now create a table like this. So for example, this is my table, and this table, I am writing here the object numbers. So for example, I have taken up one extra row, so one extra object 0, the first object, second, third, fourth and fifth, right? Similar ways for the columns, I have added up an additional column, 0th column, and then for the capacity of the knapsack, I will divide the capacity into 1 unit cells. Okay, so this is when the knapsack capacity is 1, this is when the knapsack capacity is 2 units, and 3, then 4, then 5, then 6, then 7, then 8, and 9. So we are having 10 columns with us right now. Now what I have to do, that I have to write the profits and the associated weights here. So I'm writing WI here. So weight for the first object is 1, this is 2, this is 3, this is 4, and this is 5. And since this object is imaginary that I have taken up for the computational purpose, the weight I am putting here is 0. Similar ways, I need to write out the PIs. So PI again here will be 0. Here the PIs I can find out from this P vector, which will be 1, 2, 4, 5 and 6, right? Now what I need to do, that as I can see here, the first row and the first column here, I'm going to set up with the values of zeros. Why I'm filling up the first row with zeros? So reason is that the first row denotes the profit which I am making when I am encountering different capacities of the knapsack. So if the capacity of the knapsack is 0, okay, and I'm talking about only one single object, which is the object number 0, which does not exist here, then since there is no object, what profit I can make with that is 0 only, right? So there is no object when I'm talking about 0th object, there is no object. So this object does not exist, so there is no profit associated with it, right? That way I'm writing the profits here as 0, right? And similar ways, if I talk about this column, so this column represents when the capacity of the knapsack is 0. So if your knapsack cannot hold any weight units, then what will happen, that if I pick the 0th object, how much profit I can make up? 0, right? For object 1, so when I'm picking up object 1, its weight is 1, but the capacity of the knapsack is 0, right? So I cannot put 1 unit weight into a knapsack which is having a capacity of 0, right? So again I'm writing it 0. Then if I pick up an object whose weight is 2 unit and my knapsack capacity is only 0, then in that case this object can also not be accommodated into the given knapsack. So again I have to write 0. So for this reason, all these entries I need to fix up to 0, right? Now for the other cells, how we are finding out the value? So there is one intuitive way to find out, is that, for example, the columns represent the different capacities of the knapsack, and I need to solve the problem when the capacity is 9, right? So where I'm going to find out the solution? In this column. So this is the column where I'm going to find out the actual solution of my given problem, but I'm going to solve it for each and every sub problem here, right? Now for the first object, or this row, the second row, when I come here, okay, now I have 2 objects open with me. One object which is imaginary one, which is not having any weight or any profit, so it is not, adding it up is not going to change anything here. Now the second thing is that the other object, the object number 1, when I'm adding it to the knapsack, the capacity is going to be reduced by 1 weight unit and the profit will be increased by 1 unit, right? So since I only have 2 options here, either I can add object 0 and I can add object 1. How I'm going to, find out the maximum profit here? So for example, if my knapsack capacity is 1 unit, so I can accommodate an object which is having 1 unit weight here, and what profit I can make up here? Maximum is 1. So I can only add this first object here and it will satisfy the constraint of weight capacity of the knapsack, and then I will get 1 unit of profit here. For example, if I go to this column, it says that the maximum weight that I can put inside the knapsack is 2 units now, but since I only have one object which is having a weight of 1 kg or 1 unit, for example, I only can put up this one single object here and can make the maximum profit as 1 only, right? So this way, whatever the capacity is right now of the knapsack, whether it can carry 8 kgs or 9 kgs, whatever, But since I am only open with only one object which is having a weight of 1 and a profit of 1, I can only add up that object to the knapsacks, right? So the maximum profit that I can make up here is only 1 unit. Now, once I come to this row, this shows that now these 3 objects are open to be accommodated inside the knapsack. Since we are not talking about the 0 object, because adding it up is neither increasing the weight or the profit. So I'm only talking about these 2 objects which I can select to put up into the knapsack to find out the maximum profit, right? Now, for example, if the capacity of knapsack is 1 unit and I have 2 objects, one is having a weight of 1 unit, the other one is having a weight of 2. So I cannot put up here this object. Okay, what choice I have? That I can only add up an object which is satisfying the capacity or criteria of the knapsack. So what maximum profit I can make up? 1, right? Associated with this object. Now when the capacity increases to 2, now I can add either this or I can add this into the knapsack. Now where I am getting the maximum profit, I can manage to get a profit of 2 units when I'm adding the second object here. And as you can see that we cannot add up both of these objects into the knapsack, because the current capacity of the knapsack is only 2 units. And if I add up these 2 objects together, the weight will become 2 plus 1, which will be 3, and that will exceed the capacity of the knapsack, right? So again, for weight unit 3, now there are 2 options. I can add this up, I can add this up, or I can add both of these if they are satisfying the capacity constraint. So as you can see here, that if I add up these 2 weights together, I will be getting a 3 unit weight, and the total profit that I can make up here, I can find out it by adding up this and this profit, right? So 1 plus 2, the maximum 3 profit I can make up here. Similar ways for 4, again, there are only 2 options. So maximum profit is 3 for, so this way I'm going to fill up the table. Similar ways, if I come here, then another object will be open to me, so I can select between 1, 2, 3 and their combinations that I can add up. And when the weight unit is 1, only 1 can be added. When weight unit is 2, only 2 can be added. And when weight unit is 3, for 3 I can add 1 and 2 together, or I can take up 3 individually. So either I add these 2 together or I add up this. That is satisfying this capacity of 3 unit. Now, where I'm getting the maximum profit? So if I'm adding these 2, I'm getting a profit of 3 units. But if I add this single object, I'm getting a profit of 4, which is maximum here. So 4 is maximum. So 4 I will write here, right? And again, when I'm talking about this, so now the capacity increases to 4 units. So I can take up 3 plus 1 here. So 4 plus 1, 5 I can get here. Then for weight capacity of 6, 3 plus 2 and plus 1, I can take up all these. So the total profit will be 4 plus 2 plus 1, 7, right? And this will be the maximum profit that I can make up here. So that way we are proceeding here, and we are filling up the table, and where I'm going to find out the final solution in this cell. And this cell represents when the knapsack is having the capacity of 9, and we have considered all possible combinations of all the objects that we have been given to us. So the final solution will be find out here. So that way you can find out and solve the knapsack problem using dynamic programming approach, right? And another thing to get this intuition is from this equation, that I can say that to find out the ith row and wth column entry, I just need to apply this thing, and this will be equivalent to whatever we have seen here, that how we are picking up between 2 maximum values. So here either you are picking up the previous profit and you are comparing it with a new profit that you can get as a combination of multiple objects together, and whatever profit value is maximizing, that we took up and we keep it up here, and that way once we reach to the end of the table here, we will be having the maximum profit that we can make out of these given 5 objects with these value and or the profit and the weight, combinations. So this is all for today. Thank you so much.